Was it the third one that I was talking to you about?
Oh, yeah.
Yeah, that one turned out to be smooth.
Okay, good.
Yeah, but I figured it out.
All right, so please, if you could, let's turn in the take-home. Just kind of, I don't know, pass them, try and get them like this way.
When he helped me out,
Take one and then pass these back. The most fun? Is that what you said?
Most intensive.
Oh, they said most enjoyable. Did I put the wrong due date on there? No. Next Wednesday, yeah. Okay, any other take-homes? Where are they? Y'all got them over here? Okay. Thank you. Anybody else?
Oh, that's the next one.
Thank you. Okay, that's it. Okay, make sure you turn in your take-homes. And just set them right here on this corner. All right, we're gonna start a new section today, 11.5, chain rule. And there are not any notes that I usually hand out for this, just because, well, you'll see, it's a little easier to just write this by hand than it is to try and come up with a good image for it. So let's get started, all right? I will have some order to these notes, though. So first note, 11.5.1. Recall from Calculus 1, if y is some function of x, right? Then it makes perfect sense for us to talk about the derivative of y with respect to x, doesn't it? Yes? So we could ask for dy dx. By the way, did you all have a good weekend? No? Okay, I'm sorry, Kieran. You should have had it done. You should have got it done before Friday. Then you would have had a good weekend. Oh, I handed out the new take-home. I'm hesitant to say it because I said it about the last one. Like the last one, I was, oh, it's only 4 problems. This one's 6 problems. I think this one is a little more straightforward, just computational. Not as much like trying to figure out what's going on, all right? So everyone have a copy of that? Yes? All right. It's due next Wednesday. So you get a little bit of a break. Yeah. So you can start it on Tuesday night.
That's exactly.
You should be able to do that entire take-home exam by the end of today's class. Everything on there is through today's stuff. Okay, so remember that when we were in Cal 1, if we said y is a function of x, then you could actually talk about what dy dx meant. Now I'm going to start doing stuff. It's going to look a little weird at first, but you'll see where we're going with this, all right? So I'm going to draw a little picture of what's happening here. I have y, and I'm going to connect it with the line down here to x. And what I'm saying is that y is kind of higher up on this diagram, x is below it, which means that in order to know y, someone needs to tell me what x is. So if I have x, I will be able to produce y. So this is kind of like the root, and the tree is growing out of this, all right? So it makes sense for us to talk about dy dx, since y depends on x alone, right? Someone gives you x, y can be determined, right? All right. Baby steps. Whoa. Need some more room up here. Now, what if you have this? 11.5.2. What if you're given that y is some function of x and that x is some function of t? I'll do it this way. X equals g of t. So y is a function of x. Shut it, please, yes. That means if someone gives you x, you can determine what y is, right? But over here this says in order to know x, someone has to give you what? T, right? So if I try and draw this diagram again, what would be the letter that would be the highest point on this diagram? Y. Okay, so we have y. Y would depend on what? It's supposed to be straight down. Y would depend on x. And x would depend on t, right? So when we link these two variables together, right, it makes sense for me to talk about the derivative of y with respect to x, doesn't it? And when I link these two together, it makes sense for me to talk about the derivative of x with respect to t. Yes? This all makes sense? And so back in Cal 1, if we were looking right here, y ultimately depends on t, doesn't it? Since y depends on t, which you can see it from this diagram also, right? T, you need t for x, you need x for y. Then we can ask for dy dt. That would be the rate at which y is changing with respect to t. So you change t by a little bit, that changes x, in turn that changes y. So we can talk about the instantaneous rate and change of y if there's a little bit of a change in t. Yes? We good? So what is this by the definition of chain rule from Cal 1? If I want to know what dy dt is, it would be dy dx times dx dt. That's what chain rule from Cal 1 would have told us. Now I'm going to give you an example of this right after this so you can see how this works, all right? But it's almost like these dx's cancel, don't they? Dx, dx, and you're just left with dy dt. Now, back in our picture, do you see that to find dy dt, what you do is you take the product of these two down the tree? Do you all see that? Now, we only have one branch to this tree right now. So it's hard to talk about it as a tree because there's only one branch. But we just multiply these two, and that would define the derivative of y with respect to t, yeah? Okay, so let's look at a specific example of this. 11.1, let's see, we'll call this 11.5. Example 1. there's nothing new here, okay, yet. It's just a different sort of notation. Let's say y is equal to x squared, and let's say that x is sine of t. Find dy dt. So what it'll be is the derivative of y with respect to x times the derivative of x with respect to t, right? That's what I just said on the previous note. And what is the derivative of y with respect to x? So come over here, take derivative on both sides with respect to x, and what would you get? 2x times now derivative of x with respect to t. So take derivative with respect to t on both sides. dx dt is equal to cosine t. And then what we could do next is get everything in terms of a single variable. Like right now I have x's and t's mixed, right? So I'm going to replace x with sine t. And this would give me 2 sine t cosine t, right? And of course, that's an identity, isn't it? Just so happens to be. That's sine 2t. What's that? What's wrong?
There was a problem like that from the test.
Oh,
There was a trigonometric identity like that.
yes, sir. I remember.
No one believed me.
No one believed that that was true? I believe you. I believe you. Are you talking about the one with trying to find the maximum speed? No.
Yeah, it was.
Okay. Yeah, so you could use this identity or you could have not. I think you could have left it like that also and still done it. But okay. All right, so look, this all seem okay to you? This x right here? I replaced it. And that's just because I want everything in terms of t. So I just went back up to this right here. Now let me rewrite this problem in a different way, okay? I'm just change things up a little bit. What if I take this right here, okay, and I rewrite that, but let's actually just plug in x right now before we take a derivative. X is sine t, right? So this is really sine squared t. And if you were asked to take the derivative of this with respect to t, you would do chain rule, right? So the 2 would come out, be 2 sine t, then times the derivative of sine t, which would be cosine t, which is this answer right here, right? So that's this right here, what we did when we do this in Cal 1, this is chain rule, right? But now we're kind of looking at it from a different perspective. And you'll see why in just a moment. Okay, you just have to hang tight for a second. No questions? All right. So what if now 11.5.3 what if we have z is equal to some function of x and y? What do you need in order to determine the value of z? You need both x and y, don't you? So if I'm going to draw a diagram of this, I have z up top, but it depends on both x and y. So I would have to draw 2 lines coming off of this. This would be x, and then this would be y, wouldn't it? And let's think derivatives. When it came to derivatives of this from last class, we said that there were how many different derivatives we could get from this? There were 2 that we talked about. One of them was the partial with respect to x. The other one was the partial with respect to y, right? So what happens in our diagram is if we're going to try and talk about a derivative going from here to here, or a derivative going from here to here, it can't be a straight derivative like in Cal 1 because we're holding one variable constant. So we call them partials, right? And our notation would look like this. Partial of z with respect to x, right? That would be down this branch. And then down this branch, partial of z with respect to y. Does that make sense? Those are the two derivatives that are possible. Right? Those are the two derivatives that are possible. So anytime you have a diagram where a single variable needs two different variables in order to determine, right, what the value is, down those branches have to be partial derivatives. They cannot be straight derivatives like Cal 1 unless the branch goes down by itself like in the previous problem, right? Then they were straight derivatives. Got it? Okay, so let's do an example. I'll do it next to this. Example 2. Let's say z is equal to x sine xy. Oh, I've fallen behind on the homework videos. It's just been busy. I've had some things come up. So my plan is to stay after today, after class, and I think I'm going to try and do 11.4 and 11.5 homework videos. Okay, example 2. So let's find how many derivatives are possible here. 2, right? That's it. Because z depends on x and y, so there's 2 derivatives possible: partial of z with respect to x and partial of z with respect to y, right? So let's start with the partial of z with respect to x. This would be equal to, I'm going to hold which variable as a constant? Y. So that means I'm going to have to do what when I do this here? Product rule, right? So product is right here. Derivative of x is 1 times the other one, plus, now derivative of this one, cosine xy. Then go inside, what's derivative of xy with respect to x? Y. And then finish off product rule, x. We did that last class, didn't we? So this is sine xy. I think I'm just going to clean it up a little bit. xy cosine xy. Okay, so there's your partial of z with respect to x. Questions? Okay, now let's do the partial of z with respect to y. So what is it? Okay, x squared cosine xy. Do y'all agree? So x is a constant now, so there's no more product rule, right? Because x is a constant. So just cover it up, it'll come for the ride. Derivative of sine of xy is cosine of xy times the derivative of what's inside. What's that derivative of this with respect to y? Just x, right? So that pops out. But I already had an x out there, so x squared. So that's correct. Good. All right, so these two partials are different, right? Okay, so nothing new on this, really, just some different notation, having you draw some trees. So what if I tell you this? This is, now we're moving into the next note. The whole idea here is to get to a chain rule. Some way of taking derivatives of really complicated functions that depend on other functions. Okay, so how about this? Suppose you have z is some function of x and y. And, so I'm going to use comma for and x is some function of t, and y is some other function of t. What do you need to know in order to know what z is?